Electrostatics 14, field lines, flux at Gauss law. We'll continue from the previous lesson. We're talking about electric field lines. Yes. Before we wound up yesterday, we made a statement. What was that? No two field lines cross each other. Or if they cross, we would draw, or we can draw two tangents. There. And it would mean what? Two directions for the same electric field. Which is not possible. Right? Hope you understood it.
Yes.
Plus, minus if I had this one field line we told. Supposing there was one more field line crossing like that. So there'll be one tangent like this. There'll be another tangent like this. So the same point, you cannot have two e's, right? Two e's and two directions like that. That's what you mean by that they should not cross each other. Okay. Then sometimes there will be questions like this. Say I have a plus 2q charge here. Or let me say plus q charge here I have. Plus q I have. If you're supposing somebody gives like this, that there are one, two, three, 5, 8 field lines here. If I have plus 2q, taking the same scale, what? For plus q, I have 8 lines. There should be 16 lines for this because there is more charge. I don't know whether it became 16, but it doesn't matter. Why, if you ask me, you can compare the field of this with the field of this. If I take a surface which is being pierced by the field line, this is not a circle, it is a sphere. Actually, you're looking in a two-dimensional picture here, but it's actually 3D. The field lines are there out in a radial symmetry. At distance r, if I draw one sphere like this, and at the same distance r, if I draw a sphere like this, the field density will be less here, more here. So if this is E1 here, if this is E2 there, there will be less number of lines passing through the same cross section, and there will be more number of lines passing through the similar cross section. So density of field lines is more here. So E2 is greater than E1. But just only single charge is given. You simply want to get a feel of it, just draw as many lines as possible. You can draw 8 lines, 10 lines, whatever. You'll know that field is spreading like that. That's all. But the number of lines has to be proportional to the charge if you want to compare the field of this with another charge. Naturally, more charge, more field lines as compared to the field lines here. Because we already know the field of this at this point is greater from the Coulomb's law, we know, isn't it? So otherwise, remember, I can draw infinite number of lines around a charge. So particular sample rate, people call, depending on the requirement, I can decide a particular scale for the field lines and draw them for different charges. Do you follow my point? If it's only a single charge, it doesn't make a difference. I told you already, we talked about it yesterday. Even if I draw this many lines from R1 to R2, if you consider, the density of lines will be less at R2 and more at R1. Density of lines, you understand? The number of lines by area will be less here and more here. Once again, you can say E1 is greater than E2. But here, if I draw a few more lines also, it doesn't make a difference to tell a result of E1 greater than E2. Do you follow my point? For a single charge, when you want to compare the field at one point to the other point, you can choose any number of lines. That's okay. But when you want to compare the field of Q with 2Q at the same distance, you need to take a particular scale. If I draw 10 lines for Q, I'll draw 20 lines for 2Q. If I draw 100 lines for Q, I'll draw 200 lines for this. So that now once again, you can distinguish between the field of this and field of this at the same distance, for example. So this kind of a thing is required for understanding field lines. Any questions before I continue?
So will the length of the field lines matter?
Length actually, like now you should understand, field is inversely proportional to R square.
Yes.
So the field lines go on until infinity or very large distance. Okay.
Sir, then for like plus Q and plus 2Q, since it is a large distance, the length will be approximately the same.
Look, there's nothing like infinity defined, right?
Yes.
What do you say?
It's just we cannot count.
Yeah. Less than infinity, greater than infinity doesn't matter. Tell me, children. Okay.
Yes.
I'll continue then. But the way you look at it, the field lines is not a very accurate way of describing the field. Tell me. We can only say, like previously yesterday we talked, the electric field strength is proportional to the field lines, we said. Rather, field lines by area. Okay. So yes. We'll go for a more mathematical approach to the spread of field around a charge. I'll continue. In that connection, we'll introduce what we call electric flux. For a while, just forget the one field lines thing. I'll go for defining electric flux and then connect it up. So electric flux. I'll just define it mathematically and try to give a physical meaning of it slowly. Otherwise, there will be confusion. Look, in this region, there is one uniform field like this, represented by parallel field lines. Now, imagine one surface, flat surface, perpendicular to these field lines. Actually, I'll draw it. Again, that's not proper. Actually, I'll draw the surface first. We wanted there is one. It can be a real surface, like a metal plate or anything, or imaginary one, doesn't matter. Now think there's a field in this area. Like this, a uniform field. Like this. This is perpendicular to the field lines. That's what I could draw. And E is all over same. Let this area be A. Okay. You can draw many more lines, but I don't want to spoil it. Then we define electric flux through the given surface as phi E electric flux is equal to EA. The field lines still you need to think, but the connection I'll talk slowly. Field lines are there here. Field lines have to be there because we need to think that field is spreading, spreading into the space. So here, this E is everywhere perpendicular. Then flux is EA. But for example, in a particular case, if there's a surface like this and field lines are parallel to it, flux is 0. So first of all, you should get an idea that there will be electric flux. If at all, only, not if at all, only if the field lines pierce the surface, not when they are parallel to the surface. And if the field lines go through the surface everywhere perpendicular to the surface, and if E is all over constant, then the flux, the mathematical quantity called flux, is equal to EA. Okay. But how do you connect the flux to the field lines? Phi E will be proportional to the number of field lines. Look, previously E equals number of field lines by area we wrote.
Yes, sir.
Do you follow? Now E is 5 by A. There's no proportionality. Directly E equals 5 by A. Since E is proportional, when we said E is proportional to the number of lines by area, when you write E equals 5 by area, I should also be able to say 5 is proportional to the number of lines, isn't it?
Yes, sir.
Now, why am I telling it so much is, generally people have a misunderstanding of saying that number of field lines itself is flux. Number of field lines itself is flux. You can call, once you choose a scale for one charge distribution, another charge distribution, you can say this so many field lines are there, 1000 lines is a flux, you can say, but it doesn't serve any purpose. It serves only the purpose of comparing field of the two charges at the same distance, for example. After that, no. Right? But this is more accurate definition for replacing the field lines. We'll get an idea of how the field is spreading into an area by defining electric flux. This has its origins in velocity flux. But I'll come back to that. There will be confusion otherwise. Just take it this way, like a rule-based approach. Let us follow. After that, I'll come back for more elaboration of the same idea. But once you're comfortable with that, even if you don't go, it doesn't bother. Doesn't matter. But let me see. So flux is 0 here. That means field is not piercing through the surface anywhere. It's all parallel.
Yes, sir.
But now, supposing I tilt this area. I tilt this area. In the same field, how many lines will pass now through the tilted area? Same number of lines or lesser number of lines?
Less.
Lesser number of lines will pass, isn't it? Actually, to understand that, you can put one more extra line there and see one more here. Uniform, of course, the distance has to be same, parallel lines. Now, when I tilt it, lesser number of lines, fewer number of lines will pass. Lesser number of lines will pass through the area. Through the area we choose. How many lines will pass? Do you know? I'll show you. Just to draw a projection of this area. What is projection? Shadow. Huh? Hello?
Yes, sir.
This is the projection of the area. So that many lines which are going through the projection normal to it will pass through this. Do you follow my point? So we are slowly giving the meaning of the flux there. Like I'll write lesser number of lines will pass, or that many lines. I'm expecting you to write all this. That many lines which are passing through the
normal projection.
Passing through the projection. Of course, they'll pass normally now. The whole idea of drawing projection is that only.
Yes, sir.
Passing through the projection normally, of course. I'll draw few, but remember, if this angle was 60, if these lines were 500, for example, now there'll be 250 lines passing. This will be what? A cos 60, this area, or in general, A cos theta, if it is theta. Huh?
Yes,
Hello?
sir. Yes.
So I'll just show only a few lines.
So since it is half of the original area,
Yeah, A cos 60, this is A by 2. So the
yes,
flux will be A by 2 into E. Or in general, flux will be EA cos theta. Flux is basically a mathematical replacement for what? Number of lines. Because number of lines is very subjective. There's nothing like fixed number of lines we can draw anytime. We can draw as many lines as we want. Say if you're drawing it on a paper by some method, how sharp your pencil is and how much time and patience you have got. So that many lines you can draw. So to remove that whole idea from the subjective nature, we went for defining a mathematical quantity called flux, which is E into A basically. But still that will be similar to the field lines only. Field lines idea and the flux idea are similar. This flux will be more if charge is more. Similarly, field lines will be more if charge is more. But slowly, we'll take it once at a time. So flux, if all the field lines are normal to the area, EA we told. But the total flat area is now bending with the bending, less number of lines are passing, then the flux will be written as EA cos theta. Have you written down everything, children?
yes.
Now, I'll continue. But the moment you got something as A, B cos theta, we tend to think in terms of dot product, isn't it? Now, look at this. This is our tilted area. And we have its projection, right? This is all projection. Okay. Now, I will not draw many lines because that becomes crowded. This is E. E is same everywhere. Now, this area from your vector idea, we know if vector A, vector B are like this, if angle is theta between them, this is A cross B, right?
Yes, sir.
This is nothing but area vector. Isn't it so?
Yes.
Geometrically. So if I have this area like this total area can be represented by an area vector which is normal to the surface. This is my area vector. if this angle is theta, children, you will also see that this angle also will be theta. And we said this was a cos theta. And we said flux through the actual surface is Ea cos theta, we told. Huh? Do you follow? Therefore, now in general, I can say flux equals E bar dot A bar. In other words, of course, it is very useful, advisable to think of the projection, but otherwise you can just not bother about projection. Simply take the area vector and multiply with the E vector in a scalar way, dot product way, that should give you the flux. But the problem comes, will the area going to be all the time flat like that? And will it be all the time open? That is, you can have a closed surface area also, isn't it? Huh? So therefore, we define elementary flux d phi and then integrate. Like, what do you mean by that? Hope people understood this. I'm waiting for you to write. Children.
Yes.
Yes.
I'm waiting for you to write. Here, remember, this area is flat. Everywhere the angle between area vector and E vector is theta only here. Okay. But area can be of any shape. In general, area can be of any shape. But even then, we don't bother. We'll take an elemental area. Of course, drawing that will be not easy. I mean, remember, area is somewhat in some zigzag way. So this will be divided into many elemental areas, small areas. Like that. And we choose a particular elemental area like this. And give it a direction again as dA. Now dA is as flat as this bigger area. I don't know whether you understood. I bent the area. Do you follow here? The
Yes,
skin-like thing which was bent like that. So area is not going to be flat. As a whole, it is curved, right? So
Yes.
in that curved area also, I can imagine such a small area. You can divide that into many small areas and consider a flat area. This is so small that the curvature is gone. Do you follow my point?
Yes, sir.
So, and E is there all over, wherever. E also need not be constant like that. So if this at this point, if this is E, if the angle between them is theta, d phi we can calculate is E bar dot dA bar. In fact, it is actually going to be like this. You take the component of area along E. Or you might even say component of E along area. Doesn't matter. If I take the component of area along E, I'll get that old idea that I'm talking of the what you call perpendicular area, which is pierced by the E. So therefore, this is d phi E equals E bar dot dA bar. Now I want the flux of the whole area. total flux would be phi E, that is integral E dot dA, integrated over the surface. Of course, if it is a closed surface, to get the flux to the whole surface, we'll put a thing like this circle there. But this still I put it an open surface, doesn't matter. So we went from easy way to most generalized way of defining electric flux. Tell me now.
Sir, so here for each dA, we'll take the perpendicular component and add all of those perpendicular components.
Yeah, you can take E cos theta along dA, you can take. Or dA cos theta along E, you can take. Doesn't matter. Dot product is A into B cos theta, B into A cos theta, right? Huh?
Yes, sir.
Remember, this will be very, very important because we'll be talking about Gauss law in a very thorough way. This is still an open area I put, children. Do you follow? Huh? So flux through this area I wanted to simply integrate E dot dA. Huh?
Yes.
Hello. But flux through a closed surface, when you take surface, the elemental area dA, dA's direction, elementary area dA's direction is always along the outward normal. Here, this d I could have taken this side also, actually speaking. This is an open surface. Still I put open surface here. So in that case, I could have taken dA even below. This way also I could have taken. It doesn't matter because which is outward is not a well-defined thing. If I take dA this way, I'll get the flux positive. If I take dA this way, I'll get the flux negative. So for an open surface, there's no way you can define which is positive, which is negative. But once I take a closed surface, the same thing, for example, I think of a closed surface like that. This is three-dimensional, children, once again. My dA should be this way only all the time, along the outward normal only. Do you follow? So this is my E, for example. So d phi will be E dot dA. Phi will be, or phi E, you can write integral over the closed surface E dot dA like this. Come on, there are 1, 2, 3, like that. Many points were mentioned. Tell me, children. Hello. First, try to understand the algebra of the flux. Huh? What do you mean by that? If I have a surface like this, if all the field lines are, look, I hope you are able to see, this is a flat surface. Now this, my pen is the field lines representation. Let me make a hole here. So you have maximum flux now. Can you see this? Huh?
Yes.
But this is bent like this. Flux becomes less. Do you follow? But in spite of it, remember, field lines will pierce through the surface. It is becoming like there's no piercing is happening. There's no flux, right? But the surface is somewhat bent like this. So nowhere the total area, if I take, it's not going to be perpendicular or anything like that. So I'll take one, this open surface. I can take one dA here. dA's direction I can give either this way or that way and find out E dot dA over a small surface, integrate to get it for a full surface. Now close the surface. Close from all the sides, this side, that side. Okay. For example, this is hemisphere. If I have one more hemisphere this side, that will be closed. So I cannot take the area inside. When area direction inside, I should take area is area. This is dA. If I take dA this side, ds this dA this side as well, the same dA. But now the direction should be taken along outward normal like this. E dot dA you'll find out here, and over the whole surface integrated, you'll get the flux through the whole surface. So that's what I meant by the algebra of the flux. I have not connected it yet to charge. I was only trying to tell you that number of lines by area is the density of lines. The density of lines is more, E is more in that region, we say. But the density of lines is only a subjective thing. So instead of saying number of lines by area will decide E, we'll say that there's a thing called flux that will decide E. Instead of saying number of lines by area, flux by area we do. But how do you define flux? You define it as basically EA. All right. Now to understand this thoroughly, I'll show you one or two examples, even before connecting it to Gauss law. Hope everybody followed these main ideas here, simple ideas. For a closed surface, our elementary area's direction is always along the outward normal only. And you should also remember, for any area, you can think of a projection, and this projection will be if E is piercing through this projection normally, simply that E into the projection area is what we call flux, which in mathematical terms is put as integral E dot dA or E dot A if E is all over same. So can I continue?
Sir. So to properly define the strength of field, instead of field lines,
number of lines by area, we'll say flux by area.
Yes. So instead of lines, we use flux.
Yeah. Right. Now I'll talk a little more. I mean, I'll go even for the how this idea got originated from the fluids also I can come, but let people feel comfortable with the rules of the game first of all. Look, the very first question I will be this. have one E like this in a region of space. Remember, this is all 3D, not just in the plane of the surface here. Now, in this, if I imagine one hemispherical open surface, this all surface, everything, this one is the surface we are talking. But this is open side. E is same everywhere. Hello.
Yes.
So flux through the hemispherical surface is how much? Flux through the hemispherical surface is equal to how much? We've got the basic method of doing it. From E dot dA, isn't it?
Yes.
Flux equals integral E dot dA. This is the basic definition of flux, surface integral. Of course, this is dA, this means surface integral. Over the surface, you need to integrate it. Look at this. Of course, ultimate, I'll give the radius of this to be R. We are going to show it finally like this only, E into pi R square. Either plus or minus, depending on which way I took my normal. I told you this is still open here. It's not a closed surface.
Yes.
So depending on which direction I'm looking at the area vector, it will be plus or minus. Because remember, for this cap, this hemispherical cap is pierced by the lines in not in a normal way, isn't it? The lines are all parallel, right? So they're not perpendicular to the surface anywhere, isn't it? But look, for this projection, they are perpendicular. Hello?
Yes.
That's why in the beginning itself, I put like that. Flux is that. E into the perpendicular area. But here, this actual area is not perpendicular to the field lines. But what is perpendicular? The projection. So E into the projected area, which is perpendicular, is what you call flux, which comes from here itself. Look at this. I'll show it for doing future things later, better way. Though the answer is over already. Let us just imagine one ring. Hello. That ring, how will you describe that ring?
Yes.
Look, this is theta. This is d theta. The edge of the ring, this edge is making theta with this one. The other edge is making d theta. So that this length, this width of the ring is r d theta, where r is the radius of the hemisphere. Okay. Hello.
Yes, sir.
Now, if I take my area vector this way, and in that also I can take a even smaller area, delta A. This whole thing is what? dA. It is coming from that side also, remember it. Hope people understood what is this ring business. Have you? So,
Yes.
but this area spread all over, whereas I wanted a small area. So here also I will take the delta A, not dA. I can take the area vector to be like this, or I can take that to be like this, doesn't matter. This is my delta A. And this is my E, right? So what is the angle between E and delta A here? If this is theta, tell me children, this is 90 minus theta, right? Hello.
Yes.
This is
90
90 minus theta. So how much is this?
90 plus t.
90 minus 90 minus theta, isn't it? Huh? Hello, children.
Yes. 90 plus theta.
Yes.
90 plus theta. Actually, I would have avoided this 90 plus theta business if I took the delta A inside, because that way the angle will be only theta. Do you follow? Hello. If this delta A, if I choose this way along this one, this would be theta only, right?
Yes.
For an open surface, you can take that to be any, there's nothing like outward normal, isn't it? But to get into the mood of taking it all the time along the outward normal, I'm taking it like that. So this one, so delta phi will be what? E delta A, what? Cos
Cos of 90 plus theta.
90 plus theta. How much is that? E delta A cos 90 plus theta. Minus cos theta. Hello. Cos
minus
90.
sin theta.
Sorry. Sin theta, right?
Yes.
Raviteja Muddu, you are coming now. You will be in trouble once again later. This is sin theta minus. Okay. Now, like this for delta A all around the ring, if I take d phi will be what? Minus E delta A sin theta, because all the angles, this whole thing is symmetric about this. So theta will be same, everything is same. So I'll get what? Minus E dA sin theta. Delta A plus delta A plus delta A will be dA. Hope people followed. Right?
Yes.
Hello. This delta A is a small element of the ring. So if I add E delta A sin theta, E delta A sin theta, E delta A sin theta, I will get E dA sin theta. What is dA? Look at this. This is R d theta, the width. And this radius is how much, children? If this is R, if this is theta, this will be theta, right? So what is this radius of the ring? R cos theta.
R cos theta.
So the length of the ring is 2 pi R
Cos theta.
cos theta. This is R cos theta. Do you agree? Hello?
Yes.
So 2 pi R cos theta will be length of the ring and R d theta is the width. So dA will be what? 2 pi R cos theta R d theta, right? Hello? Huh? People are worried because I'm doing a lot of maths. So if I come here, I'll write in white here, separate it from that. So d phi will be finally what? Tell me. Minus E dA. 2 pi R cos theta R d theta. 2 pi R square.
Sin theta.
This is what?
Cos theta d theta. Yes.
Cos theta d theta into sin theta, isn't it?
Yes.
Right? Hello?
Yes, sir. It becomes sin 2
Sin 2 theta. So what do I get? D phi equals minus E phi R square
sin 2 theta d.
sin 2 theta d theta. So flux the whole hemispherical surface will be phi equals minus E into pi R square can be taken out, isn't it? All constants. Integral sine 2 theta d theta from where to where? How does the variable change now? What are the limits? How do I get the full ring?
Sir, 0 to pi.
0 to pi
Pi.
or 0 to pi by 2? You tell me. Hello? Others. It's not only Sriya in the class. Vamshi, Trishul.
Pi by 2.
Trishul says pi by 2. Sriya says pi. So you need to decide. All right. Tell me, why did you say pi and why did you say pi by 2? Because this is going to be actually main problem in deciding the limits in many cases. You remember when you decide, choose your limits, that should cover the whole element, right?
Sir, pi, because if we start at one end as 0, then we need to go to the other end, so that will be 180 degrees.
And you, Trishul?
Sir, we are taking ring now.
We are taking a ring, right?
So
Okay.
it will be from down to up.
The largest ring and the 0th ring, zero
Yes,
radius ring, isn't it?
Yes, sir.
So theta equals 0 will cover what ring? The bottom ring.
Bottom.
Full ring it will be covering, isn't it? Sriya?
Yes, sir.
Now, for mass people, all this is very, very important. I rubbed it off. Now, what is the integration? Phi equals minus e into pi r square. Integral sine 2 theta d theta is what? 1 by 2
Minus cos theta.
minus
Cos theta.
minus cos theta. Is that right, everybody? Between 0 and pi by 2. What am I getting now? E into pi r square. Just check if there is any calculation mistake which is going to happen. Cos 2 theta from 0 to pi by 2. That will be E into pi r square. Cos 2 theta. That is how much?
1 plus 1.
Pi by 2. If I put 2 cancels. Cos pi. Is it minus 1? Huh? Hello? Hello? 2 into pi by 2. 2 cancels. Cos pi minus 1. Minus cos 0. 1. Well, there was one more 2 somewhere. You forgot 2.
Denominator 2 is there.
2 is there. So what am I getting now? Minus E into minus we got because I took the area upwards. If I took the area downwards, I would have got plus only. For a closed surface, that's not a big deal. No, sorry, for an open surface, you can take either this way or that way. Now, what is happening? Do you understand? Hello? Do you follow what is being done here?
Sir, we took for one part of a ring and then made it a ring and again took many rings.
Complete the calculation. Let us see. Oh, it's already time. Yeah, complete it. Remember all this. I'll be coming back again. I mean, with same thing. Complete it. But I told you already, if I took dA this way, I would get plus. What you need to understand is this. If I take dA like this, E like this, I might have taken the component of E along dA or component of dA along E. Do you follow the point? Hello. EDA cos theta is that finally. Complete it, children. Tilak Patel, you are coming and going out. Even before I finish the lesson, people are dropping off. That's bad. Right? There will be many more questions just only on flux. I'll be showing you them tomorrow. Then after understanding flux somewhat, we'll connect flux to charge and that becomes Gauss's law. Okay. So for today, I'll be closing this. But already it's not a big deal here. Like if you can all the time get the projection, all the time it's not possible, but many a time it may be possible. You'll take a projected area which is pierced by our E normally. So that E into that normal projected area is what we call flux. Okay. All right.
Thank you, sir.
Thank you, children.